In the remainder time, let me just give you a couple of examples of using the hash table, leveraging that it's very good at handling the dictionary type of operations efficiently. Okay, I would also talk about some of the downsides of hash table. Again, as we said earlier, the hash table is mostly for dictionary queries. And among them, the most important one is this membership query, namely search to see whether an element is a member in your set or not. Okay, so if you have a problem which essentially only requires this dictionary operations, membership queries, insert and delete, then you can potentially use the hash table to get a very efficient expected running time. So let's see that, remember that we have this movie problem where you're given a list of the lengths of movies. Okay, you have a whole bunch of movies and you know their running, their time, the length of each movie. Okay, I say they're stored in some array movies, and you have a flight duration D. And what you want to do is that you want to figure out whether there are two movies from your list whose total length exactly equals to D. Okay, otherwise you return none. Okay, so this was the movie problem, right? And we've seen before that the naive algorithm would take quadratic running time, because in naive algorithm, we simply take all possible pairs of movies and then add up their lengths to see whether it equals to D or not. Okay, so since there are quadratic number of possible pairs, that takes worst case quadratic running time. And in fact, if you do if every pair is equally likely to give you the final total length D, then you do expected running time analysis, you will find out that the expected running time for this naive algorithm also takes quadratic time. Okay, so there's it's not helping. Okay, but earlier, after we talked about sorting, we said that we can do better by first pre-sort the array of movie lengths. Okay, after we sort them from small to large, then remember that we say that you can actually check, given each of the movie X, okay, what you can do is that if there's another movie whose length add up with the X length to D, then that means that the other one, the length has to be D minus length of X. Okay, so what you do is that given each movie X, you simply go to the sorted array. Okay, you simply search for, so this is array A, you simply search whether you have another movie whose length is D minus the length of X. You simply perform a search in this array. This is an array of sorted array of movie lengths. Okay, that's it. So now pre-sorting takes time and log n if you use the best algorithm, the merge sort. Okay, and to search, this is just a binary search in a sorted array, and this takes time log n for each query, for each movie X. So in total, I have to do pre-sorting, then I have to search for every movie, each of the n movies, so that's n times log n, and the total time as such is still n log n. Okay, so using sorting idea, I could search for such a pair of movie whose total length is D in n log n time, okay, instead of quadratic. So this is improvement, okay? And what are we going to do now is that you recognize, okay, for each of this movie, check whether there exists another one whose length is D minus length of X. Essentially, it's a membership query, it's a search problem, okay? So intuitively, if I instead use a hash table, then the search can be done more efficiently than in using binary search, which is log n. Okay, and indeed, that's what we do. So I don't need to pre-sort the all the movie times at all. Okay, and I'm going to organize all the. So this is the list of input of movie times. Okay, So I first insert, so this is just to insert all the movie time into a hash table. Okay, so this is insert all movie times into a hash table. Okay, then for each of the movie in the hash table, okay, so sorry, for each of the movie in your input list, you compute what is the target, which is the d minus the time of the present movie time. Okay, so then you search, is there a movie of this target length in the hash table? And this is a membership query. Okay, and yes, if you found it, you simply return it, so you found it. If not, if after you check all the movies, you still didn't find it, then you return none. Okay, so what is the expected time complexity? Well, the expected running time is that, so expected. This, we're performing, essentially, we're doing an insertion, okay, and that is order of n because it's constant time each and you have linear number of them, okay? Now, this for loop is going to iterate over each of the n movie in your list, so that's going to run n times. But within each of them, I only have this membership query. And now the expected time for this membership query is only constant. That means that after checking for all the n movies, the expected time is linear. So the total expected time as such is linear plus linear, which is only linear. Okay, again, the saving comes here. The saving comes out using hash table. I can do membership query only in constant expected time. And also, since I'm using a hash table, I don't need to pre-sort the list of movie times. And pre-sorting itself also takes n log n. I don't need to. I only need to insert them into the hash table, which is also linear time. So the whole total expected running time is only linear. Okay. All right. So it's also very easy to implement. Okay. Here's another example. Okay. Now we know that the two words, or in general, two strings, W1, W2, are anagrams if their letters, the letters of one can be permuted to get the other string. Okay. So for example, eat and T is anagram because both of them consist of just letter EAT. Okay. Listen and silent are anagrams because both of them only just consist of letters S, I, L, E, and T. Okay. Let's say that now the problem you're given is the anagrams problem. You're given a collection of n strings. Okay. You're asked to determine whether any two of them form a pair of anagrams. That's what you want to do. Okay. All right. So how do we solve this problem? Again, you can first spend a couple minutes to think yourself. Well, the observation is that because the strings that are just the permutation of each other, okay, that means that if you now sort both strings, or sort all the letters alphabetically, then their sorted list has to be exactly the same, right? So EAT and TEA, if you sort them alphabetically, then you have A, E, T, that's all the capitals inside. This one, when you sort it alphabetically, is A, E, T. Then they're exactly the same. Okay, so if you sort them, then you should get exactly the same sorted list. Okay, you can just check whether the sorted list are the same or not. Okay, and this gives us an idea. Okay, maybe, so our problem is that we have a list of n strings. We want to know whether any two are anagrams or not. Okay, then maybe I can do is that I can just simply store them in a hash table. Okay, store all this input n strings in a hash table. Okay, and the way that they're going to be hash to the same position is if they have the same sorted string, okay? And if any two ever got hashed to the same position, then I know that I have an anagram, okay? So that's the idea. In particular, what are we saying? So here is an algorithm, okay? I'm going to use this SYN, which is a hash table, which is a set in the Python, but implemented using hash table, okay? So our input is this is input, which is an array of strings, okay? Then for each of the word in this list, okay, I first computed the sorted list, okay? Then I simply insert this. I check in this list of strings that I've already seen, is W is inside, okay? If it is in, then that means that I've previously had another string which had the same sorted list as the current one. So I simply return true, okay? If I haven't seen this before, then I simply insert it into my hash table SYN, okay? So for example, if I use the previous example, let's say that you're given eat, silent, and then T. Okay, what do? When eat comes, I first compute its sorted list, which is AET. Then I use a hash function to hash this one into a specific position in the hash table. This is my hash table SYN. And then I link AET here. This comes from eat. Okay, then silent come. Then I compute its sorted list order, which is EILNST. Okay, then let's say that we store it here. EILNST. When T comes, I first compute the sorted list. And then now when I hash it, I go to the same slot. And when I go to the same slot, I already have someone there, which means I already sent another string which has the same sorted list. That means I found an anagram. So we don't need to proceed any further. We just return true. That's it. Okay. What's the running time of this? Well, there are n words in this list words. For each of them, assume that all the words is only constant length. So sorting takes constant time. Okay, so we assume the length of the words is only constant. Okay, then this is just a membership query in the hash table. So this takes constant expected time. Okay, in other words, this total time is constant expected time, and we'll have to do this n times. So overall, we again have linear expected running time. Okay, and of course, you can think offline that if you don't use hash table, if you use other data structure, how much time you would your algorithm would be. Okay, but as we can see that using hash table, you can solve this very efficiently. Linear time is pretty much the optimal because you still have to scan the list at least once. Okay, all right. So these are how the hash table can be used to help us. I mean, again, it is very effective when you have dictionary type of queries. Okay, but that's also the problem of the hashing, namely, it's only efficient for membership query plus insertion and deletion. Okay, if you have other queries, then hash table may not be efficient. Let's say that suppose you you want to solve instead of finding two movies whose total time is exactly D, you want to use find the two movies whose total time is closest to D. Okay, unfortunately, the hash table is not effective for that. Okay, another example is that let's say that suppose you want to support a maximum. Okay, you want to say I want to find the maximum of all the key values stored in my hash table. Okay, this unfortunately is not a membership query, it's not insertion deletion, and in fact you would have to then scan through all keys to look for the one that's has the highest value. Okay, so hash table is not good for maximum query. Okay. Because of the same reason, the hash table is also not good at performing a range query in the list of numbers. What that usually means is that, let's say that you want to return everything within the range, say A and B. Okay, the reason that it is not effective for that is because in general, if you want to have an effective algorithm to solve this, what you want is that once you find one element inside, you want to be able to quickly find all the other elements within this range. Okay, but the hash function, as we said, it actually that for two neighboring number, let's say that if you have 10 and 11, okay, but the two neighboring key, they can be hashed to very different hash values. Okay, so you lose this locality in the hash value. Okay, so even if you know where 10 is hashed to, doesn't mean that you can efficiently get information about where 11 is. Okay, so the hash table in general is not effective in performing this kind of range query. Okay, which is very common, very important in practice. While on the other hand, the binary search tree, for example, can be modified, augmented to perform range query very efficiently. Okay, the binary search tree can also solve the example 1, finding the two movies whose total time is closest to the in n log n time as well. Okay, because it's a more powerful data structure. Okay, all right. So as I mentioned, part of the reason is because the hash table doesn't have locality. Okay, similar items from your universe can be mapped to very different bins. Okay, so in the previous example, when I used the modular, that's not a good example. They still look similar. Similar items can be mapped to similar. In fact, even with the previous example, let's say that we look at our hash function from the natural number to from 0 to 10. Okay, remember our hash function is basically x mod 11. Okay, now imagine that I take element 10 and 11. So 10 got hashed to 10, but 11 got hashed to 0. Okay, so 10 and 11 are neighbors to each other, yet their hash value are very different. Okay, so you don't have this locality. Okay, so this very often is not this no locality is important behind the idea of hashing. Okay, because especially for things like cryptographic hashing, you don't want similar things to be mapped to similar places. Okay, so this is kind of essential, necessary in order to spread items evenly out in your hash table. Okay, but in practice, very often if you do a query, okay, if you search for a specific element, then it's very likely you're going to search for another element which is neighbors of the previous one. Okay, so in practice, you actually want to be able to, when you search for elements that's close to each other, you want to be able to retrieve them faster. So you hope to have this locality, which hash table doesn't provide. Okay, but nevertheless, if the type of queries you are interested in is mostly just membership with some insertion deletion, then hash table is a very practical and efficient data structure. Okay. Yeah, well, I should point out that because they don't have the locality in practice, since we often query similar objects continuously, okay, but then in the hash table, they may store in many different places, okay, and if your hash table is large, this may mean that you have to keep access different parts in your array and then cause them cache misses. You have to reload a different portion of your array into your memory, okay, which can make it slow. Okay, yeah, just to summarize, hashing is a very useful idea that actually, the idea essentially is to map a potentially large and complex object, but to a simple, smaller signature, okay? Could be a number from 0 to 10. And a hash table is a very practical data structure for dictionary type of operations, okay? And especially if you assume that the size of your data is kind of proportional to your hash table size, then all of the operations can be done in constant expected time if I assume the hash function is good. Okay, and this is particularly useful when the number of keys that necessary in your data set is much smaller than the size of the universe. Okay, like if your size of universe is the all possible integers, but in general, you're only interested in a small subset of numbers. Okay, so here it's much smaller than the universe. Then using the hash table to map this huge infinite size universe to a smaller hash table is make it very economical. You don't have to open a larger array for the potential, the part of the universe that you're not going to see. Okay. In practice, of course, that one has to choose the hash functions properly so that to make sure that it hash elements intelligently spread them out. Okay, so as I said, there's a separate, very deep subjects that we're not going to cover in this class. Okay, but in Python, as we point out already, both dictionary and sets actually implemented use hash table. They're very practical data structure. All right, that's all that I want to talk about. Again, there's an actual office hour today at 7 p.m. Pacific time, and good luck with your first midterm.